Weinberg from Charlotte, and the title, Your Attention, Please. Your Attention. And the title is Necklace Graphs and Slowing Down the Flight. Please.
Do you know if I need to turn anything?
Yes. Okay, but it's on. I think
It's on. Okay. So this is a joint work with Professor Molchanov, and this is the first thing which I would like to mention. Maybe second thing. First, I would like to thank organizers, because as everyone, I enjoy this conference very much, and they took care about everything, about place, weather, company, talks, nice talks. And so thank you very much to all the organizers. And my talk concerns the contents of my talk is here. It is 3 points, and I'm sorry why I did that. It is 3 points, and the new results only in the section 3, and what I will discuss about sections 1 and 2. These are old facts, old results, our results, but I need to remind them, and besides, I think perhaps it would be nice to repeat them in any case. So we came to that point to discuss graphs from practical point of view, because we were attracted by an applied problem of slowing down of light. I will discuss what does it mean a little later, but let me mention immediately that at some it is exactly in 2004, maybe earlier, but we offered a device for a slowing down of light, and this device had this configuration. This, we called it a necklace type device. When you have a thick or fat graph, and these loops have different lengths of upper and lower part, and it is periodic, not exactly periodic, but truncated periodic graph. So it means that you have some number, capital N of periods, and then wires which are connected to something else. So playing with these lengths, difference in lengths, L1, L2, L3, which are repeated periodically n times, we hoped to have a device which will work for slowing down of light. Again, slowing down of light, please, I understand that no one can slow down the light. I'm talking about using some wording which is usual in physical community, and which is related to the slowing down of the wave packets, not slowing down of the phase velocity. At that time, 2003, 2004, we were absolutely sure that if you consider a propagating wave in such a waveguide, then due to the continuity of the field and flux, you will get a limiting problem on the graph with standard Kirchhoff condition of continuity of the field and flux. And so we even did not ask ourselves, is it true or not? We are absolutely sure that there are no other options. The field is continuous here, it has to be continuous here. The fact that you will get usual ODE on the graph is more or less obvious. The only difficult question is what type of gluing condition to impose on the vertices of the limiting graph. So we are absolutely sure that continuity here leads to continuity here. Why, I don't know. We were so sure because, of course, everyone can imagine sequence of continuous functions which converge to a discontinuous one. And this is exactly what happens here, in fact. So, and this was our starting point to think about what type of gluing, we called it gluing condition. You can think about boundary condition, matching condition, whatever. Have to be imposed, I'm sorry, have to be imposed on the vertices of that particular graph. What make our problem different from everything which was before us is the following thing. We consider the wave problem, a wave problem. And it means that we really would like to know propagation of waves in our structure, not on the graph, but in our original structure. And it means that equation which we consider is negative delta u minus omega squared u is f or 0, whatever. So we have this parameter. We have equation with a spectral parameter omega, and this is a very important difference compared to what sometimes is considered, because if you think about a parabolic equation and solve a parabolic equation, and then you will get e to the power negative delta t phi, and if you're thinking about long time behavior, you need to know the lowest eigenvalue of operator delta, and that's it. But if you are dealing with a wave problem, then the situation is completely different, and you need to know the whole spectrum. You look for time harmonic waves, for example. You come up with Helmholtz equation, not with you deal with Helmholtz equation, not with the Laplacian. So what is our original problem? The original problem is Helmholtz equation with f or with 0 in most part of my talk in the domain. I'm sorry, this picture appeared to already 5 or 6 times in my somehow every paper which we started with that picture because we're too lazy to change it. So an example of a graph, and you have cylinders and junctions which connect this network into this waveguide in network, and the boundary condition can be arbitrary. It can be Dirichlet boundary condition, Neumann boundary condition, or Robin boundary condition. And the topic of the goal, our goal was to find out the limiting behavior of the solution of that problem when epsilon goes to 0. So one more time, the difference is mostly related to omega squared, but also in fact the importance of the in choice of the boundary condition also significant. So it can be arbitrary boundary condition. So this is an example, particular another example of that graph, and the limiting graph is here, and let me also immediately mention that in our consideration it is not important whether the graph is bounded, relocated in bounded region, or has infinite leads, infinite half cylinders. And by the way, for bounded graph, you still will need something related to unbounded graphs, unbounded structure. It doesn't matter whether you started with a bounded graph or unbounded. I decided to stress it because in our publication somehow it is written let M be the number of half cylinders, but M can be 0. Okay, so assumptions under which I'm going to discuss the problem would be self-similarity of junctions, it was already mentioned today, so I assume that junction can be obtained by rescaling of epsilon independent junction, which can be avoided, but it's somehow easier to assume that. Let me mention that not the whole picture, but only junction itself can be rescaled, because if you rescale the whole picture, the length will become instead of finite, instead of being 1 over epsilon. From here it also follows that cross sections of the cylinders, cross section of waveguides, also can be rescaled from the epsilon independent domain. Now, it was discussed here a couple of times how the spectrum of the problem of operator H sub epsilon looks like in that type of domain. And by the way, for simplicity, I will restrict myself here assumption that in fact in all the cylinders have the same cross section. In our first publication in 2006, we did not assume that. We have a complete description of absolutely general situation, and even in the first talk I even tried to explain the general situation, and now I understand that I was very stupid trying to do that. So let me restrict myself to a very simple case. All the cross sections are the same, and I will make one more simplifying assumption for my talk in a minute. So let me remind you the spectrum of that problem of operator H sub epsilon in L2 of omega epsilon. The spectrum, to get the spectrum, you need first of all solve the problem in the cross section. So you solve eigenvalue problem in cross section first after rescaling when there are no epsilon. Lambda sub n are eigenvalues of the problem in the cross section. I hope it is clear what I'm doing. I rescale cylinder, I take this domain U, and we solve the problem in that domain. And then we solve the same problem in the thin domain of diameter epsilon. And then you will get negative Laplacian applied to phi of y over epsilon is equal to epsilon negative 2 lambda j phi j lambda j epsilon negative 2 phi y over epsilon. So as a result, you will get the following picture that on the spectral parameter, spectral axis lambda, you have these important points, lambda naught over epsilon squared, lambda 1 over epsilon squared, and so on. These are eigenvalues of the problem in the cross section, and spectrum would be absolutely continuous starting from lambda naught to over epsilon squared to infinity, with multiplicity 1 here, with multiplicity 2 here, with multiplicity 3 here, and so on. It was mentioned already in the talk, in a couple of talks, in particular in the Grisser talk. If you deal with graph which is bounded, no semi-infinite parts, then spectrum is discrete, but still these points are limiting point for discrete spectrum, and that is why they are very important. And so I will call this number threshold. So threshold is the low h of the continuous spectrum, or the first point, limiting point for discrete spectrum. Yes, it is not limiting point. I'm sorry, it is not limiting point. Of course, spectrum is discrete, but I mean the limiting point from point of view that when epsilon goes to 0, the eigenvalues approaches to that point, move to that point. When epsilon goes to 0, you have points which moves in that direction. After rescaling. Yes. After rescaling. Of course, I do it in a time. One time I do this explanation. Next time I put epsilon negative 2 delta. I'm sorry. Yes, epsilon negative 2 delta equal minus lambda squared, and then these points became lambda naught, lambda 1, and then everything is different. Okay, I hope it is clear. So I'm going to make one more restriction for my talk. Again, let me repeat that only for purpose of simplicity. I will assume that omega squared is here. That I will assume that that omega squared in this region. In this case, you have only one propagating mode in the cylinders. Only one propagating mode in the cylinders. And this propagating mode, perhaps it is written somewhere, so let me show it. First of all, in each cylinder we will use coordinates y in the perpendicular direction, z along of the axis, and this one mode in each cylinder is eigenfunction in the cross section times exponent plus minus I sigma z, where sigma is square root of omega squared minus epsilon negative 2 lambda naught. So this is a solution, eigenfunction of continuous spectrum. I mean, of eigenfunction of continuous spectrum in the cylinder. If I consider omega, which is slightly bigger, which is such that epsilon omega squared bigger already, not just lambda naught, but bigger than lambda 1, then you will have additional eigenfunctions and so on, and picture became a little more complicated. So let me again restrict myself to a simplest situation. Now, many particular cases of the problem were studied. I mean, this V means problem of limiting process when epsilon goes to 0. In the case when epsilon omega squared is close to the threshold or lower than threshold, and I believe that this our result of 2006 were the first results where that problem were studied under conditions that omega squared is to the right of the threshold, and this is essential new assumption which we made, and and that is why results are different. So I did not, by the way, this list of course is not complete, and by the way, in the previous talk today, Olaf Post put another list, and intersection is very small. I do not remember if you have dots as I did, as I do. And of course, I'm talking only about this limiting procedure, not about anything else, because if you think about all the facts related to the propagation of waves and so on, then, for example, previous talk has to be included here, and some other paper by Boris Pavlov and some other people from here. But I'm talking right now only about limiting process. so the main result, which I would like to remind, is written here, that that scattering solution and the resolving of the operator can be approximated by corresponding solution of the one-dimensional problem on the limiting graph with the gluing condition expressed in terms of scattering matrices of the individual and extended junctions. And I would like really to talk about what is so different in that statement to some very similar statements before, because it was a lot of results related to the scattering matrices of the quantum graphs. A lot of results related to scattering matrices on the quantum graph, and how these scattering matrices were constructed before us. The usual approach, which I'm aware of, was always the following. We consider the graph, then we imposed gluing conditions, for example, Kirchhoff, or arbitrary self-adjoint extensions. Then we solve the problem, and then we consider coefficient of the solutions and affinity and construct scattering matrix. So you start with gluing condition and then construct scattering matrix on the graph. So what is different compared to what I aware of is that we do not start with a gluing condition. We are doing something different. We start with a thick graph, and we have scattering matrix on that three-dimensional in real life domain. And using that scattering matrix of three-dimensional domain, we define gluing condition on the graph. And this is what makes it different compared to what it was before. And let me, yes, this is a definition of what does it mean, scattering solution on the thick graph. Everyone knows that, but let me remind, if you have a thick or fat graph, you put an incident wave, find solution which has a form of incident wave, which is plane wave times function in the cross section, and reflected wave with some coefficients, and this coefficient form scattering matrix. So the scattering matrix is defined by the thick graph, by the three-dimensional domain. There are no gluing conditions at all involved here. Continuity, of course, there is a continuity, because solution which we are looking for is a smooth solution. It is infinitely smooth everywhere. It's a solution of elliptic equation. And this solution defines scattering matrix. This matrix is unitary and symmetric. And this matrix will be involved in the boundary condition on the graph. In fact, this is result of 2006, but somehow I believe that at that time it was not clear for everyone, and maybe even we didn't understand well enough why we need to somehow promote this fact. I'm sorry? Yes. Unitary and symmetric. And this is, by the way, very important that it is unitary, not orthogonal, orthogonal, I'm sorry, not orthogonal. It means that eigenvalue, this complex matrix, it is symmetric without complex conjugation, and it is unitary eigenvalues. It means I'm sorry that Tij is equal to Tji without conjugation, and it is unitary. It means that eigenvalues are complex valued. The absolute value is 1, but they are not necessarily plus or minus 1. Okay? Yes?
What is the meaning of symmetry? Something
Uh, yes, I think it's something like that. Yes, yes. The proof is one line from green formula, but I think it is true. So you have this matrix, and then the main result will be stated on the next page. But roughly speaking, the main result that scattering solution can be approximate. Oh, it's very difficult to push a right button. Okay. In roughly speaking, the main result is that scattering solution is approximated by scattering solution of the problem on the graph, of course with sigma with spectral parameter reduced by the what was taken by eigenfunction in the cross section, and gluing condition defined similar to what usually is used in self-adjoint extension, but in self-adjoint extension people put here arbitrary matrix A, B, symmetric or whatever with some properties. My point is that you in fact have to have a specific matrix here. The combination between derivative and function is given with help of the specific matrix related to the scattering solution. And what is also important, that you don't need to solve the problem on the whole network. That these coefficients are defined locally by individual junction. They depend on the shape of the junction. When people start to have self-adjoint extension, they already do not remember that this graph is obtained from a domain with a junction which has a specific form. And now this is how this form of the junction is involved in the construction. Again, so I need to explain the meaning of what is here. First of all, V indicates that we are talking about vertex V. And I need to explain what does it mean psi V and TV. And for that, I will do it on example of necklace graph. So in order to, if you would like to put gluing condition at that point, can you see you have three edges here? We construct vector components of which are values of the solution on that edges. It is vector with three components. Then we take one junction which is related to that point, and consider extended junction. So we extend it up to infinity all the ends. Okay, and then we solve scattering problem for that extended junction. It means that you can put wave through any of the three channels. You have 3 by 3 scattering matrix. Okay, and this individual junction and scattering matrix of that junction gives you the coefficient in the boundary in the gluing condition. Okay. So this is one more time the same condition. Can you see one more time? This is a function, it's derivative. This coefficient 1 plus TV, this coefficient identity matrix minus TV, and TV has to be evaluated at a specific frequency which is related to that construction. It depends on epsilon and omega. To be more accurate, TV depends on epsilon times omega, but you also have coefficient sigma here. Do I have formula for sigma, or need to go back somewhere? This is the sigma. Can you see it depends on original frequency minus something which is taken by the eigenfunction in the cross section. So boundary condition depends on everything. Boundary condition depends on everything.
If this matrix is inevitable, can you take inverse?
Yes, Yes, it is analytic matrix. It is analytic with respect. Okay, no. 1 plus t can be degenerate. For some reason, I corrected the file, but forgot to copy the correction. So it has to be here. If this matrix is not degenerate, then you can write it in that form. So, by the way, thank you for paying attention to that, because I will work with that form of the boundary condition. I will invert that matrix to write it in that form. A is inverse to that matrix times the second. It is written here. What does it mean? What is important that this coefficient A, matrix coefficient A, is real value, which is easy to see if you reduce that these factors to a diagonal form. Then y plus such an exponent, or y minus such an exponent divided by y plus such an exponent is real.
It's because separated so conjugate.
Yes. So I will work with that matrix, but let me again stress that this matrix is not taken from the error. It is defined by the scattering matrix of a junction of a specific form. Okay, now, for some reason, my talk could be prettier because it was colorful, but now it is only black and white. I don't know why, because I put a lot of red and white colors here, but it is not seen here. And I was so proud because I'm not so good with computers, but and I spent so much of my time on that. Yes. Yeah. Yes. Let me mention right now that, because I was going to talk about that just about here. So usually you can invert that coefficient if you are working inside of that spectrum, because why to expect the eigenvalue to be exactly -1 if it can be arbitrary function on the unit circle. But as soon as you come to the threshold, at threshold, this matrix became orthogonal, and eigenvalue of that matrix became ±1. It is only on threshold, And as soon as you have eigenvalues ±1, of course, first of all, you have to avoid that form of the boundary condition. You have to work with that one. And what you will get, because of eigenvalues plus and minus 1, you will see immediately that boundary condition are some number of Neumann condition and some number of Dirichlet condition at the end point, at the vertices. In some basis, you have to choose a basis in the some combination of the restriction of the function of the edges is 1 and is 0, and some combination of derivatives is 0. How many ones and zeros you may have? Whatever you may have, all the functions are equal, and combination of derivative is 0, 1. If you have, if here all the eigenvalues are 1, let me see. No, all the eigenvalues are -1 except 1, which is 1. Then you will get Dirichlet boundary condition everywhere except one condition, which will be the Neumann condition. But you may have two combination for functions and two combination for derivatives if you have 4 leads. So you may have all the options. Now, which option you will have in reality? We studied that question also in 2006. By the way, after Olaf Post paper, because he first, I think, who solved this type of problem, which I consider right now for Dirichlet boundary condition. He studied specific situation related to the asymptotics of eigenvalues near point lambda naught, near threshold, and show that for the Dirichlet boundary condition, the limiting problem is a Dirichlet problem under some assumption of the geometry of the body, of the junction. In the Neumann boundary condition, the Neumann boundary condition is very specific one, and I think it was clear from the talk of Olaf Post, and the Neumann boundary condition was studied a lot, although again in this case lambda naught is 0, and a Neumann boundary condition was studied near point lambda is 0. If you take Neumann boundary condition but lambda to be positive, then you are again in our general situation. As soon as Neumann and lambda is 0, then this problem was studied. Okay? And so we made a full investigation of what may happen and show that geometrical assumption is not relevant, which was in Post paper, but everything is defined by that matrix. How many plus and minus ones do you have? And in the Neumann case, and it depends on the multiplicity of the ground state. And in the Neumann case, you will have always ground state of multiplicity 1 because there are no eigenvalues below 0. And in the Dirichlet case, you may have eigenvalues below lambda naught, and that is why multiplicity of ground state can be arbitrary, and you may have whatever you please. And in generic case, you will have Dirichlet boundary condition. So this is something not related to my today talk at all, but because some question, I answered that. So let me move. This is a rigorous statement about convergence. So convergence of the scattering solution in fat domain, the scattering solution of fat domain converges to the scattering solution on the graph times function in the cross section with remainder which decays exponentially, and this so this is true on that interval where you have only one propagating wave. And what I also would like to mention that this convergence result is valid on the whole interval up to some set. I need to put away some set on the spectral axis of very small measure, but this set depends on epsilon very badly. So this set exponentially small in measure, I need to take all the eigenvalues which are inside and drop them, because if you have a resonance pole, you cannot talk about convergence of the solutions. So you have to drop exponentially small neighborhood of poles, and these poles run as a crazy inside when epsilon goes to 0, so you have to exclude them. Okay, similar result is valid not only for the scattering solution, but also for the solution of arbitrary equation with right-hand side, for the resolvent, not necessarily for the scattering solution. My point is, even if you solve inhomogeneous equation, delta u minus omega squared u is equal to f, on that particular graph, and you take epsilon going to 0, as a limit you will get solution of the limiting graph of specific form, and boundary condition for the solution, any solution, not necessarily scattering solution, is defined by the scattering matrix. So scattering matrix responsible for the gluing condition for all solutions. And it is true for bounded graph and for unbounded graph. Okay. Now, if no questions about first part, yes.
What you tell us was discovered in the 40s by the engineers who were devising the radar. And if you want to know more about it, you can have the book, which was probably classified in some countries. I don't want to say the name, because the result of the, not the Manhattan project, but the MIT project, and it is called the Radar Handbook, where people like Bethe and Schwinger have solved exactly such problems. And there is a beautiful little work by Bethe in which he takes a waveguide, you call it whatever, that's a waveguide, and there is a diaphragm with a small hole. And he computes the transition matrix, the reflection matrix, in this case it is 2 by 2, from very beautiful consideration of the induced magnetic pole, which oscillates and then radiates. So many of the things which you are saying here were actually done and are still done by engineers. That's how they define. You have a transmission point, a T-junction. Every junction, if you buy it in the shop, you get a little drawing which tells you what is the scattering matrix as a function of the frequency.
Yeah, you know.
And even more because there is absorption. And then everything which you say doesn't apply, but never mind, it's not unitary. The other point which I would like to make is that you can get very similar effects by taking graphs and turning them into scattering into vertices. Take a graph, any graph that you want, metric graph, shrink it into a small domain of size little r. Connect to it several vertices, you have a scattering matrix. The effects which you talked about the resonances, whatever the elements that you have to remove, are in the domain 1 over r. But the matrix itself that you get will depend very smoothly on k, on the wave number, only out of these little resonances.
Yes.
But it can be as complex as you wish.
Yeah.
Okay,
So-
so Uzi, I feel that we are entering discussion. Let's.
You said you wanted to ask about the first section.
Yeah. I ask myself, so I do not have anyone to blame but myself. By the way, I believe that this notion, this fact was somewhat known to someone, maybe not to someone, but to many people. And when we did that, I even thought something that we knew that, but you know, knew and have a mathematical justification is somewhat different. Okay. So I see that I have only 6 minutes left. It's awful. I will try to speed up. And now, so the question is about slowing down the light now. And what do I mean under slowing down the light? Usual situation with slow down the light device always related to the periodic media. So I will go very fast because 6 minutes is a really short time. The periodic, if you have a Schrödinger equation with periodic potential, you may construct a spectrum which has band gap structure. You may construct block solution. So block solution are solution of the form periodic function times exponent, and shift in shift in x by period. This is periodic, but if you shift by period the whole product, it will be solution will be multiplied by that exponent, by corresponding factor. And if you consider now time harmonic function, you take this block function multiplied by exponent, you will have block wave which has the following structure. It is usual plane wave times modulo with amplitude which is periodic in x. So Bloch solution with dependence on time is usual plane wave with periodic amplitude. And let me show you that phase which defines the velocity is equal to the period times omega over k, and omega is usually very big, and if it is related to the electromagnetic waves, for example, and no one can do anything about it, this wave propagates very fast. Now the idea beyond the idea how to slow down the propagation of a signal, they use wave packets, and wave packets is a combination of plane waves with frequency supported by small interval around omega naught, and when you consider such a when you consider such an integral, you may write it asymptotic expansion of that integral, and solution will have the form of product of standard plane wave times some another function, which is Fourier transform of that cutoff function. And so solution has a form of a product of two waves, one which propagates as usual with phase velocity, and another it is also propagating wave, but it has different speed of propagation, which is called group velocity, which is related to the wave package. And this group velocity is easily evaluated, and it depends on the derivative of that number function k. So it can be found in any. Why I do not see this picture? Oh, because no color in my picture. So this is a standard picture which usually can be seen, but not on my slide, how this wave propagated. Usually it has to be a wave here, very fast oscillation here, which goes with the speed v, and which is modulated by another wave which going with the speed of the group velocity, related to the group velocity. So the idea beyond all these devices, find a periodic media for which group velocity is small, and use it in order to pass the information. And I didn't mention that, but this is an important problem for synchronizing electronic and optic, to use optical lines for fast propagation of the signal, and then slow down in order to be able to put it through computer. So one need to find a periodic media with small group velocity. This was the goal, and this goal was many devices were proposed, and all these devices were dropped out. They did not work, mostly because people forgot about the following thing, that device is not periodic, device has finite size, and you need to also think not only about how to slow down the signal, but how to put the signal in. And it happens then when you have a finite device and put signal in, then for frequencies which signal slow down, it reflects, it doesn't go in. So you really in fact need two features. One is slowing down, and second is the group velocity has to be small, and second is the reflection coefficient has to be small. And I have only 1 minute left, so I need to jump from page 14 to last page perhaps. So we found a formula for
high group velocity.
Hmm?
High group velocity.
Yes, right now, yes. So what we are doing is, first of all, we find an explicit formula for the reflection coefficient for the truncated periodic media, it depends on how many periods do you have, and this is what the formula for the reflection coefficient. So you really, what do you need? That monodromy operator squared minus 2 has to be small. And the second property which we need is that the group velocity is small, and for that for the group velocity to be small, the derivative of k has to be big. So two properties which are in reality contradict to each other. And for this necklace type of device, I really go to the very end right now. For this type of device, we evaluated this explicitly using this graph approximation. We evaluated explicitly the monodromy operator, and it has a very complicated structure where Mn depends on the scattering matrix, on matrix A, and find out parameters L1, L2, L3 for which you will have these both properties. And happens that these two properties are valid. This is the last slide, okay? So this is the last slide. And this, it happens that in the plane tangent sigma L1, tangent sigma L2, there is only one point where you have to, which you have to pick up, where the curve on which reflection coefficient 0 only touches the curve where you have a pole in the Hill discriminant, and near that pole the derivative is small, and that is why if you live nearby, then you have a small area in which the both reflection is 0 or very small, and transmission reflection is 0, and group velocity is small. So you really can construct this device. The only thing is to find that point, you really need to know the metrics. And what I would like to mention also in answer to your question, we deal with our optoelectronic center and try to create that device. And somehow, first of all, we have a very strong optoelectronic center. They don't know how to deal with this Mach-Zehnder interferometer with split signal through this. They measure only, they even don't know how to measure. They may measure only amplitude of the scattering matrix, not phase.
No.
When we talk them, please give us phases.
I'm experimentalist.
Yes, and you can measure phases, but maybe you can do that not on that scale.
Not on optical.
Yes,
on
not
microwaves.
not.
On microwaves, there are machines. You can buy a machine which measures the amplitude and the phase.
No, they told us in order to measure, they may measure only shift of the phases, not phases. And as soon as they put something nearby, they change phases. So we cannot find the general language with them. And okay.
Okay.